share my PPT now.
Okay, sir. I'll check it, sir.
Sir, is my PPT visible, sir?
So no, sir, it is not visible, sir.
I don't know. Only my blank screen is visible, sir.
Yeah, I can see D, sir. D, letter D on screen.
I don't know. I don't know how to bring my PPT. One second, sir. I'll
Are
try to
you there?
share.
Okay,
Sir,
sir.
I'm
You
there, sir.
share your screen
Yes, sir.
and
I'm.
then just tell me, sir.
I just close my PPT and I come back, sir. Once again.
Okay, sir.
One second, sir. No. Entire screen. My PPT is not coming in my window.
So before that, let me give
One
the
second, sir.
briefing, sir.
So once again, sir, I'll try to share my PPT once again. There are some issues. Then we can.
Okay, sir.
Layout full screen. I think my PPT is not sharing. I don't know why. I think I'm doing the correct one. So even now PPT is not shared, sir.
Yes, sir. It is not visible, sir. I think it takes time, sir.
I think. Should I pin my screen, sir? Yeah, just type. I pin my screen.
Yes, sir. You have to pin your screen, sir.
Yeah, I
Then
pin my
only
screen.
the
That's why it is
presentation will
showing
be
D. I pin my screen. That's why it's showing D. But my sharing window, it doesn't. My PPT doesn't come up. The entire screen. I don't know why is it. Sir, no, still on.
Screen is visible, sir.
now we can see your screen, sir.
PPT is visible, sir.
No, sir. PPT is not visible, sir.
You open the
Now it
PPT,
is.
right? Yeah, now it's fine.
Yes, it is visible, sir.
No, PPT is open, sir. Okay, sir. Okay, sir. Thank you, sir. Now is it visible, sir? Sir, PPT.
Yes, sir. It is visible. Yes, sir. It
Sir,
is visible, sir.
so does it show machine vision for wireless system startups?
Yes, sir. Yes, sir. Yes, sir.
Okay, sir. Okay, sir. Thank you, sir. Thank you, sir.
Okay, sir. Okay, sir.
Thank you, sir. Sir, in case of any non-visibility of PPT, please let me know, sir.
Okay, sir. Sure, sir.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
And
Badri, sir, we can start the session.
okay,
Okay, sir.
okay, sir. Okay,
Sir, in
Good
case
afternoon
of
to
any,
everyone.
thank you, sir. Thank you, sir. Please continue, sir.
Okay, sir. Good afternoon to everyone. I welcome you all for this presentation in the field of development of ECE Panimalar Institute of Technology, Chennai, Tamil Nadu, in association with IEEE, TEMS, Madras Chapter, PIT, EDC, IIC, IEEE, SB, IETE, ISF, welcomes you all for the AICTE sponsored short-term training program on mission vision on wireless sensor system startups. I welcome our chief guest, Professor Dr. M. Prem Kumar. He has completed his doctorate in the field of wireless communication in Anna University. He is having more than 17 years of experiences, and he has published more than 15 papers in reputed international and national journals and conferences, and he has research fellowship in Anna University. I welcome you, sir, and I'm glad to hand over this session
Thank
to
you, sir. Thank
Professor
you.
Dr. M. Prem Kumar, sir. Thank you, sir.
Good afternoon, present here. Sir, am I audible, sir?
Sir, you are audible, sir. You are audible, sir.
Okay, sir. Okay. And my PPT is also shared now, sir? Okay, sir.
Sir, it is visible, sir. It is visible.
Okay, sir. Okay, sir. Thank you, sir. Okay. So I'll start this session. So good afternoon, one and all. So the topic for today's presentation in this AICT sponsored Sttp is machine vision for wireless system startups. So as you know, machine vision is one of the hot topics which is nowadays in accordance with the thrust areas suggested by AICTE. So they have given artificial intelligence, data science, and all these. So all these topics are under the family of machine vision. So now what I'll do is today I'll try to add another possible area where you can do some possible research. You can become entrepreneurs. You can go in for startups by adding on wireless systems. Okay, of course, all these concepts are coming under embedded systems. So I'll specifically go on into by considering any wireless setup and explore what are all the possibilities which you can have in startups. What are solutions you can provide? So what are the front end and what are the back end? That is what I'll try to go on. Okay. So the objectives of this particular presentation. So as you know, I have told that it is machine vision wireless systems startup. So to help researchers in academia, industrial sector contributing to machine vision. So by machine vision, we know that through use of smart cameras or cameras used in our any personal digital assistant like mobile or what to say or an iPad or something like that. So we can go in for some product based development or we can give some solutions for any application. That is what the main objective is. To analyze wireless systems for startups, so analyze its pros and cons. Then contribution towards research and development in wireless systems, machine vision for industrial product development. So wireless systems based startup relating to machine vision, you can either go in as a software based approach or you can either go in as a hardware based approach. That is what I intend to tell. So my presentation outline is that so I'll consider a wireless system, machine vision based wireless system layout. Then I'll let you know what is the architecture. Then I'll let you know what is the various possible solutions you can provide from wireless systems back end side. That is, I'll mainly try to concentrate on the back end side of any wireless system. So after image acquisition, back end of a wireless system. So front end will be mostly a radio frequency RF. So easy engineers will be knowing what is RF and what is back end baseband. Then I'll let you know what are these startup schemes, probably in one or two sites in central government and state government sectors. Then probably the pros and cons. So this will be my presentation setup actually. So as an introductory slide, so I have given these the basic definitions for startup. So startup, incubator, what is an incubation? So far up to the past 3 days of this STTP, so various experts, various expert speakers have given the definitions for startup. So a startup actually it is nothing but it is a temporary business model. So startup is basically a temporary business model. So you can have either a single entrepreneur or multiple entrepreneurs to develop a unique product or service and obviously market it for commercial viability. That is what I mean by startup. So a startup, you can have a startup by using an entrepreneur from an entrepreneur, or you can have some investors. Okay, so investors with a potential idea where you can market it with for some possible business opportunity. So as you know, startup according to various definitions, various definitions. So it is a temporary business model. So most of the startups just take off, or due to some lack of funding, or due to some other financial possibilities, it might continue or might not continue. Okay. So for a startup to flourish, so startup comes from an entrepreneur. For a startup to flourish, you need to have a supportive form of incubators. Okay, so an incubator is nothing but a B school, or it is a non-profit oriented organization. So just like as you can have an incubator to be in any private organization or a college or an institution, where they'll offer space for entrepreneurs who intend to start startup, and they provide some financial funding. So mainly it is non-profitable. So we have to be very clear on these particular terms. So this slide will be probably just a supportive one to the various topics so far we have seen in this particular STTP. So incubators, they offer a free space, mentoring, office space, and seed funding. So seed funding can be either through angel investors, or you can have some crowdfunding or whatever
Hello, sir. Your voice is not audible, sir. Hello.
might be the possibilities you can have. So then, business incubator. Am I able to? So am I audible, sir? Am I audible,
Now
sir?
you are audible, sir. Yes, sir. Yes,
Sir,
sir. Now you are audible.
actually, my network connection is causing these problems, sir. Actually, I lost my connection. Actually, so
Okay.
is my screen
Yeah,
shared, sir?
yeah, yeah. It is
Yes, sir.
visible, sir.
Yes, sir. I think I lost my connection. That is the problem. Okay.
Okay, okay, sir. Okay, sir. Okay. Sorry,
So
sir.
okay, sir. No problem, sir. So please let me know, sir. So for how many
Okay.
minutes was the call disrupted, sir?
Sir, no Prem, sir.
No, no,
You
sir.
can go
One,
ahead.
one. You
One
can
second
go,
only it
sir.
was,
Only.
your audio was muted.
Ah.
You can go ahead.
Okay. Thank you, Arun, sir. Thank you, Badri, sir. Thank you. Thank
Okay,
you.
sir. Thank you, sir.
Okay. So incubators, business incubators, they differ entirely from research and technology parks. So considering a startup, so then a startup is mainly uh, startup by entrepreneurs, or to support an startup you need to have incubators. So incubators will be normally mostly non-profit organizations, and there are various factors governing the market consideration growth. And you have various, as I said earlier, so you need to have proper crowdfunding, or you need to have low seed funding from any family or friends, or whoever it can be, or angel investors. So angel investors, as it is known that they are wealthy investors. Angel investors are wealthy investors who contribute to seed funding for a particular startup. So these terminologies we need to be clear. What is a startup? What is an entrepreneur, and so on. So as our government has started a startupindia.gov.in, so we can look in for various startup schemes. What are the various possibilities of funding we can have? Okay, so you can just go through this site for further information. I'll go to my next slide. So, regarding today's topic of discussion, so machine vision wireless system startup. So, machine vision startup, or a startup, is a company. So, it is a project undertaken by an entrepreneur to provide a problem to a solution. It can be either a low cost feasible solution, or it can be any viable solution which the particular entrepreneur seems it is marketable in a particular business market. Okay, so it has to be scalable economic model, and initially a startup is always considered to be a temporary one. Okay, so machine vision wireless system model, as you know, you can it is actually a concatenation of two different branches actually. So one is machine vision, so you can provide straight away solution by using the concept of image processing and its allied areas through machine vision. Or if you just combine machine vision and wireless system, you can provide back-end solutions through the startup under the name of machine vision wireless system startup. Okay, that is what I intend to tell. So I will not be going much in detail into the image processing concepts, which we have seen for the past 3 days, which various expert speakers have given. I will just go on to the other possibility, explore the other possibility of providing possible solution. Okay, so machine vision startups. So it is a new business that intend to grow large beyond by a solo founder or multiple founders. Okay, so but the fact is that machine vision allied startups, they face high uncertainty. So in case if a particular student wants to have a if he has an idea,
Sir, your voice is not audible, sir. Hello? Hello?
if he wants
Sir, your voice is not audible, sir.
to make a startup. So the first thing is that he will be unaware of what to do.
Hello, sir. Are you there, sir? Participants, please wait. He will be reconnecting in a few minutes. Participants, sorry for the inconvenience. He will be joining in a few minutes. Participants, due to some network connections, he can't able to connect. So please wait. He will be reconnecting soon.
Sir, is my screen visible, sir?
Yes, sir. It is visible, sir.
Okay, sir. Okay, sir. Okay, sir. So we'll continue further. Uh, so the machine vision system model for any startup. Okay. So first you need to have sense the image. So the imaging data will be considered from the camera, and imaging data will be captured and considered. And here you have the unlocked digital conversion. So here you have the
Sir,
unlocked digital
sorry for
conversion. So
sir,
unlocked digital conversion is
sir, sorry for
sir,
interrupting,
it is.
sir. We
So
can't
tell me,
see
sir.
your slides, sir. We can't see your slides, sir.
Okay, 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 sir. One second, sir. One second.
Okay, sir.
Sir, is my screen visible, sir?
Yes, sir. It is visible, sir. Now it is visible, sir.
Okay, sir. Okay, sir.
Okay, sir.
Sir, my signal is getting connected, sir. That is why the problem, sir.
Okay, sir. Okay, sir.
Okay. So we'll see this machine vision for system model for startup. So you have the camera, the image to be captured in the camera. then it will be sent to the AD converter. So in the AD converter, you'll be having sampling quantizer and in the encoder. So and it will be sent to the frame grabber. So where the data will be broken up into a number of frames. So from the frames, so the frames can be sent into the processor for further processing, and then it can be saved in the RAM location of a particular system or your mobile or something like that. And then you have further processing operations to be done. So this is normal conventional machine vision system for any startup. Actually, you'll be having the various interfaces and the robots, so to do various operations for doing any particular task. Okay, so we'll go to the next slide. So there are various types of machine vision based systems. So you have smart cameras based machine vision processing systems. Then you have PC based systems, and then you have special purpose vision appliances. So the smart cameras based machine vision application systems. So processing an image capture is done on the camera itself. So this is a cost effective system. So everything will be done within the input and output sections and the memory section present in that particular camera itself. Now, whereas in PC based systems, so you need to have an extra software. You need to have an extra software where it is highly customized. Okay, so highly customized through any particular platform. Okay, so you can capture the image, you can process, and you can further retransmit. Okay, then you have special purpose vision appliances. So where is that the case of a wireless USB, and we have various different transceivers for Bluetooth transceiver for plug and play based operations. So you can have either of these three possibilities. Okay. So now, if you take machine vision wireless system layout, so you'll be having a radio frequency section and you'll be having a baseband section. So in communication perspective, you have RF section and you have baseband section. So the RF section, the prime components are antenna, low noise amplifier, high power amplifiers, up down converters. So what you can do is that in case if you have a machine vision based startup, so if you capture the image, so if you capture the image and if you want to retransmit further, so you can go in for any design product of these particular RF components. You can have antenna amplifiers in the transmitter or low noise amplifier at the receiver. Then you can have up down converters. So you can provide solutions for transmitting any images via the machine components for the next baseband section. Whereas in the baseband section, you'll be having the prime DSP components. You'll be having the processor, you'll be having the A to D converters, and then IF section demodulators and detectors. So machine vision wireless system layout or for any particular startup, so you can work on these two particular areas: radio frequency section and you can work on baseband section. So RF section, you can contribute to developing some prototypes, some products in these particular areas. And in the baseband section, so you can work on the softwares either in any platform. You can work in DSP processors or you can work in matrix possible solution and you can go in for marketing. So these are possible ways by which you can explore an entrepreneur to go in for a startup and provide some possible solutions. So this is the basic system model of an RF and baseband section. So in any RF system, fabrication of any RF system, so the RF components, you have the antennas, you have the RF amplifiers, fabrication of these particular thing, and you can go in for testing and validation in any and you have this AD converters. So these AD converters, they come under the section of the baseband section in any wireless system where you can develop some software programs for any particular application. For example, you can convert an image signal. Okay, so you can convert an image signal and you can transform it into binary ones and zeros and you can retransmit it further. So this is what you can contribute in. Of course, this is a 2G mobile which is being given. Now, in case if you consider this to be an Android mobile, if you consider this to be an Android mobile, so you can capture images, you can then just straight away submit it into the software, MATLAB software or any software which you do for Scilab or any software which you do for processing, and you can provide some possible viable solutions. Okay. Okay. Now, if you consider a wireless system, so you have analog and digital data. For example, analog data, so you have a continuous time signal. Analog data, you have a continuous time signal like this. And if you do the concept of sampling, quantization, and encoding, sampling, quantization, and encoding, so you'll be having a digital discretized data like this. Okay, so you can contribute through providing solutions by either by considering an analog signal. So this is a one-dimensional signal which you have. Now, in case if you consider an image, so if you consider an image and if you break up an image, then ultimately you'll be getting a signal something somewhat like this. For each and every gray level, you can just do mapping of the gray levels into binary ones and zeros, and you can just do processing. So there are various possible ways by which an entrepreneur can work on machine vision and contribute at the front end side and also at the back end side. Okay, so this from this particular slide, the concept of back end processing or the baseband processing starts, which I would like to stress to provide an easiest way of solution. So here, so for example, a wireless system. Okay, a wireless system, if you have a data size, for example, a voice signal, so the bandwidth of the voice signal, obviously, which we know is 300 to 3400 hertz. Approximately it is 4 kilohertz. Okay, so the minimum sampling frequency which you can have is, so fs is nothing but 2 times the bandwidth, or it is 8 kilohertz. Okay, so the number of bits per sample considered is 8 bits, for example 2 power 8, which is 256 levels. Now here we'll do a small problem, so that if you want to have some knowledge on how one-dimensional signals work. Okay. Anyway, machine vision, we will be using only two-dimensional signals. For just information, we can just have this. So what is the minimum data rate? So we are interested in data rate in all applications. So the minimum data rate is nothing but the minimum sampling frequency. So the minimum sampling frequency is obtained from here. So the number of bits per sample. So it is totally around 64 kbps. Okay. So, Badri sir, am I audible? Is my screen shared now? I just want to.
Yes, yes, sir. You are audible, sir.
Okay,
It is
okay.
clear, sir.
Thank you, sir. Thank you very much.
Okay, sir. Okay, sir.
Okay. Okay. Now we'll consider another signal. For example, an electrocardiogram signal. So the bandwidth of the electrocardiogram signal is around 100 hertz. So the minimum sampling frequency used is nothing but here it is 200 hertz. So the bits per sample is actually 8 for representing 2 to 6 levels. So calculate the minimum data rate required for transmission of ECG in a wireless transceiver. So actually it is nothing but it is the minimum data rate is nothing but it is the product of, just as we have seen for earlier case. So the data rate is the bandwidth into the number of bits per sample considered. So it comes around 1.6 kilobits per second. Then our topic of interest. So that is machine vision, that is video. So as you know, video signals, they are all three-dimensional signals. Video signals, they are all three-dimensional signals. So you have to break up the video signal into a number of frames. Break up the video signal into a number of frames. So the number of frames per second, it is 15 frames per second. So the resolution, of a particular frame, which is considered as 480 cross 640 pixels. So the number of bits per pixel for color video is 24 bits. Now, in case if you want to calculate the data rate for a video signal. Okay. So similarly, the same procedure. So the minimum data rate is nothing but resolution of a frame into number of frames per second into bits per pixel. So you'll be having the number of frames per second. Okay. So resolution of a frame is given there. So the number of frames per second is 15 frames per second. It is 15, and it is 24 bits per second. So hardly it is around 110 Mbps. So the data rate will be by far more for video signals. Okay. Now the question is that, so what are the possible ways by which you can work on video signals or image signals? So you can convert video signals or into images as frames, and then you can map these images into binary ones and zeros for baseband processing. Okay, that is what another possibility of a solution which an entrepreneur working in a particular startup can provide solutions. So this is one possible way which I would like to convey. Okay. So if you take wireless transceivers, so that's why you can work either in the RF section or you can work in the baseband section. So in the RF section, so wireless transceiver, so it is a combination of a transmit receiver in a single package. So fabricating a wireless transceiver is not that much easy. So you have to go in for some hardware oriented organizations or companies in either Bangalore or in other places where you'll be getting expertise of fabrication of chips. Okay. So wireless transceivers, so it is employed in various wireless applications such as cell phones, okay, or the olden days cordless telephones and so on. So a transceiver is always silenced during transmission and it is always on during reception. Okay. So the classification of wireless transceiver operation, so it operates either in the full duplex mode or it operates in the half duplex mode. So you can go in for programming based operations, which I'll explain later in the forthcoming slides, to go in for various programs. So the full duplex transceiver or the half duplex transceiver, as the name suggests. So half duplex transceiver, so it has only one-way communication possible for both the time slots, and full duplex transceiver. So you'll be having simultaneous transmission and reception for different frequencies or of operations. Okay, so most of these operations it will come under the satellite operations where you'll be having proper uplink and downlink. Okay. So the wireless transceiver, so it shares a particular common circuitry. Wireless transceiver shares a particular common circuitry. So you can combine a single circuitry for being a transmitter and a receiver. And the most commonly used or the possible application which I would like to stress is the software defined radio. So everything is programmable. So software defined radio, you can either work in any programming language. So you can work in MATLAB and you can just transmit and receive in case if you have a proper SDR kit or something like that. Okay. So the software defined radio, so it is a programmable radio where you can write programs for detecting the white space of any particular application for any signal transmission and reception. So this is the functional model of a software radio. So this is a well-known block schematic. So you can contribute to providing some end-to-end solutions either in the front end side or the back end side. So for example, you have source coding, you have service network support. So all these regions come under what to say the physical layer. So all these regions come under the physical layer of any wireless communication system. So as you know, source coding it is mainly used to improve or avoid redundancy. Service and network support, it's used to integrate the physical layer and the network layer. Infosec is nothing but the information security. Then you have bitstream processing. Then you have the A to D2A converters. The modem is an A to D2A converter. Okay, so in modem, so in A to D2A converters, you'll be having the RF section. So most of this is coming under the physical layer or 5-layer solutions for any particular machine vision based application. So all you have to do is you have to just convert the given video signal or an image signal into binary ones and zeros, and you have to just do processing and provide optimal solution. That will be the best option. Okay, so you have IF intermediate processing, then RF channel access. So in this particular side, we have the various attributes governing to source coding and decoding. You have audio, video. You can also audio is a one-dimensional signal. Videos, as I said earlier, it is a three-dimensional signal. You can have images. So service and network support. So it sets up control data services. So all these factors are where you can contribute to providing some end-to-end solutions. So probably I'll consider a scenario and I'll try to explain with cognitive radio, which I've given it in the later slides. So we'll go to the next slide. Okay. Now, a possible wireless transceiver classification, transceiver IC. So you'll be having to work on either 0.3 volts to 5.5 volts. So the frequency ranges from 30 kilohertz to 2.48 gigahertz. So these are the various data rate ranges. Then you have the sensitivity of minus 104 decibels with respect to 1 milliwatt. Then you have DIP package. So from a particular entrepreneur or point of view, it is not possible to go in for packaging type RF based solutions, but whereas you can contribute on some, some individual component solutions for RF. Okay, so you can develop some components, RF components, for example, RF amplifier, a low noise amplifier, or an mixer, or a switch, RF switch, to have a particular specified power, and you can provide an end-to-end market solution for that. Okay, so decibels is decibel with respect to 1 milliwatt. dBm is nothing but decibel with respect to 1 milliwatt actually. So already we have the power level in terms of watts. Now if you want to convert in terms of dBm, so you have to just take the given power in watts, you have to just divide it in 1 milliwatts, and you have to provide what is the solution in 50 dBm. So you can provide solutions for any given particular any given application with respect to RF, either in decibels or in dBm, to find out the system loss factor, insertion loss, or isolation loss, or whatever might be the phase shifter or the switch or the low noise amplifier which you are going to consider. Okay, so as I've been explaining through these slides, so the wireless transceiver, the basic block schematic of wireless transceiver, so it is actually divided into two types. So one is nothing but the RF section, and the other one is nothing but the baseband section. So the RF section, as you know, it has all the just as we have seen in the previous earlier slides. So it houses all the low noise amplifier. You have the RF amplifier mixer. So until then you have the RF section, then you have the baseband section, where you'll be concerned with only the modulation parameters and analyzing the metrics. So you can analyze the metrics for RF section in terms of fabrication, or you can analyze the metrics in terms of baseband section and provide solutions. So these are possible ways. So actually working in the baseband section will provide a low cost end-to-end solution for many entrepreneurs who want to go in for a particular startup. Okay. So this is another setup whereby you have wireless transceivers. So you have a common transceiver. So you have a low noise amplifier at the receiver side. You have a power amplifier at the uh, transmitter side. So you can work on providing proper solutions or going in for some fabrication uh, for RF section. So the RF section, you have these components, and after down conversion or up conversion, you'll be having the baseband section, where you'll be doing all the baseband processing. So you can go to either a baseband processor, either as a software solution, or you can have the RF solutions for a particular machine vision wireless startup. Okay. Okay. So as we have seen the various possibilities, so wireless transceiver, so you need to segregate whether you're going to go in for an analog signal, you're going to go in for an image signal, or a three-dimensional signal. So an AD converter, so it digitizes information, source encoder, it removes redundancy, ones and zeros. So channel coder, so controlled redundancy. So all these areas you can contribute at the backend side. That is what I would like to stress. So this is the area where the concept of the baseband section for a wireless system startup begins. So you have the correlator. So the correlator is a combination of multiplier and integrator. So you have a match filter, you have envelope detectors, decision device, and you have multiplexers. So you can have going for some programming based solutions for any particular application, either in Wi-Fi or WiMAX or any particular application, and you can provide solutions either in the physical layer, or you can go in for the cross layer or the network layer aspect. Okay. Okay. So the if you want to contribute in the wireless transceiver wireless transceiver voice transmission, of course, even though it is a machine vision, it is a video signal. So audio is always under one dimensional. So you can go in for voice transmission and you can reconstruct. So either you can develop a very good up converter, the component of a very good up converter in your startup which you plan to start, or if you have a very good idea, you can contribute to develop an up converter or a modulator in the RF section, or you can develop a down converter or a demodulator in the receiver section. So these are possible areas. So you might think that this is a particular very simple slide which we are all aware of. So what I would like to stress is, so we need to work on certain terminologies with proper ideas, and we can work towards achieving a proper solution that will contribute to a very good startup. And in case if you have a very good idea, that will be a very good innovation. So wireless transceiver ICs. So you can have contribution either in the modulation scheme, or you can have contribution in system architectures. So these are the modulation schemes which we are all aware of, which is used nowadays in present day. What to say, 5G, 5 generation, fifth generation system wireless systems, or what to say, the forthcoming sixth generation wireless systems. So you can develop to various system architectures. You can do some modifications, you can do discovery, or you can do innovation in your startup if you have a very good idea. So you can all contribute either through the architectures. So the architectures in the sense, so this will come under the RF section for any startup, and this will modulation schemes will come under the baseband section for any startup in case if you go in for a machine vision based wireless system. Then this is the commonly used on-off keying transceiver. So nowadays wireless sensor networks are used in most of the applications. So you can try to provide an end-to-end solution. You can try to provide an end-to-end solution. So this is the baseband section. This is the baseband section, and this is all the hardware section. This is the entire hardware section where you can develop some possible possibilities. So you might think that on-off key ASK is an outdated one, but even though it is outdated, for short range applications, okay, for short range applications, something like wireless personal area networks or wireless sensor networks, OK receiver gains prime importance. Okay, so short range, low power consumption of the order of microwatts. So wireless sensor applications, wireless personal area networks. So you can develop some very good ideas. You can develop some very good ideas, and you can have the possibility of becoming an entrepreneur or to have a startup. Okay, then FSK. So FSK transceiver takes this particular hardware and software setup. So we can contribute with hardware sections, developing hardware sections, but interfacing is quite a big problem. But we can develop some hardwares, and we can do some market exploration, and we can start some getting some revenues. So these are some possibilities. So FSK transceiver. So as you know, FSK is actually used in second generation communication systems, 2G communication systems. Okay, then the ultra wideband. So for wireless personal area networks, also UWB, ultra wideband transceiver. So this might sound like a particular block diagram, but we can contribute in this UWB transceiver also. Okay. So to summarize the various system architectures, so it has been given super heterodyne receiver. What are the pros and cons of super heterodyne receiver? Various IF receiver. So depending upon the case study analysis, a particular entrepreneur can provide solutions depending upon the market. So these are all the various possible architectures which now the present day market demands. So without any seed fund or a very low seed fund from a pocket money, so you can just go in for a startup. And if you go approach any business incubator or an incubator in some institution or organizations, you can go in for say a particular thing. So this is a common transceiver which do you have. So this is a common transceiver which do you have. You can contribute also in this. So the wireless transceiver applications. So these are the current wireless transceiver applications which you can contribute in the physical end. I mean the physical layer end, and also in the baseband layer end. So RF transmitter receiver IC, even Bluetooth is coming up nowadays. Then you have Wi-Fi, RFID transceiver IC. So you can all work on providing optimal solutions. So optimal solutions in the sense, you can reduce this in the RF section. You can reduce system loss. You can reduce isolation loss. So you can increase the directivity. You can contribute in beamforming. So various possibilities arise. So this is one way of going in for self-employment, which I would like to try to introduce to the faculty members and the students. Okay. Okay. So this is, for example, a low cost 2.4 gigahertz low power applications wireless transceiver. So this is easily fabricatable in a particular low cost possibility. Okay, so this is the sample 2.4 gigahertz RF transceiver. As you know, this is coming under the Bluetooth frequency range. So you can also develop a particular low cost Bluetooth transceiver in this particular range, or you can also contribute in for 5.28 gigahertz and so on. Now, as we have seen all the various concepts earlier so far, so we have seen RF section and we have seen baseband section. So the machine vision wireless system. So it takes most probably the open systems interconnection system model. So you can provide end-to-end contributions either in the physical layer, you can provide contributions in the data link layer, so you can provide contributions in the network layer, transport, and application layer. Okay. So Badri sir, am I audible for you? Is my voice audible? I think, I'm not sure. Okay. Okay. So physical data link, network, transport, and application layer. So you can provide solutions either in all these possible options. Okay. One second. One second. Am I is my system? So Badri sir, am I audible? Is my screen audible? Is my screen visible?
Yes, sir. It's visible, sir.
Yes, sir.
Okay,
It is
sir.
visible,
Your
sir.
voice is audible, sir.
Okay, thank you, sir. Thank you, sir. I lost my connection, sir. Sorry, sir. Okay,
Okay,
sir.
sir.
I lost. That's why, sir. So you can provide end-to-end solutions in this ISO's OSI system layer, which we do consider. Now, regarding the research issues, in wireless systems, okay. So you can do research issues either at the simulation level or you can do at the emulation level, which we are all aware of. Okay, so you have the physical layer analysis for wireless systems. You have the network layer analysis for wireless systems. Okay. So whether it is whatever might be the type of signal, whether it is a one-dimensional signal or it is a two-dimensional signal like an image. So at the baseband section, or at the file layer or the physical layer, so the performance metrics are probability of error or bit error rate and capacity. So these are the two most commonly used metrics to analyze the performance of any wireless system. So actually machine vision, it can be incorporated in most of all the applications, but only thing is the way you do the processing, it slightly differs. Okay, so you have to convert the image signal. You have to convert the image signal into a properly set the gray levels into a set of binary ones and zeros. Okay, so bit error rate and the capacity are the two commonly used metrics. Then regarding the network analysis, so you can contribute in routing protocols, routing algorithms. So you might think that this is a research oriented problem, but you can provide cost effective solutions. No investment, only in terms of contribution of algorithms, either at the baseband side or there is the backend side, which I try to use. Whereas if you take the front end RF section, obviously we have to do in some sort of investment for fabrication. Okay, so the network layer analysis, the performance metrics are throughput, latency, packet error, and delay. Then at the emulation level, you will be having implementation of hardware level, so DSP processor, so analog devices, Visual DSP++, through analog devices platform. Then you have Code Composer Studio. You have the Code Composer Studio for Texas Instruments. Okay. So this is one useful information where any entrepreneur who tries to market his idea can work on the baseband side, that is the backend side of any particular application, wireless system application. So as you know, wireless signal transmission. So the physical layer. So you have the wireless transceiver. You can have any device. So you have to transmit in the channel. that is, you have to transmit the signal. Only thing is the channel parameter gets multiplied here. So the alpha is nothing but the channel magnitude. It gets multiplied here. So this is a well-known information which we are all aware of. Okay. So the wireless system model. So if you want to do some programming, the backend side wireless system model, which you need to consider is, so you can have either the channel to be either a flat fading channel, or you can have a frequency selective fading channel. So flat fading channel will have a representation like something like alpha of t into e power j theta of t. So alpha of t is the magnitude response, and e power j theta of t is nothing but the phase response. Okay. Then the frequency selective fading channel. So frequency selective fading channel, you'll be having time delayed version. So this tau refers to the time delay. Tau refers to the time delay. So you'll be having the time delayed version of the signal which is being received, and you'll be having also the time delay and the phase delay in the exponential component. So all these things will be multiplied by the parameter del. So what you can do is, so you have the perfect channel, there is no channel available, then AWGN channel, additive white Gaussian noise channel. So this AWGN channel is nothing but it is the noise due to the PCB, the noise present in the PCB of our mobile, the noise present in the PCB of our mobile. So it will contribute to AWGN channel. This is not at all a physical channel, but it is a virtual channel where this the parameter, the channel alpha of t into e power j theta of t is considered to be 1. The channel is 1 actually. Okay. Anyway, I will not go much into the mathematics actually. Now what I'll do is I'll just consider a case study. Just consider a case study of the cognitive radio system. So the cognitive radio system, as you know, it is mostly used to detect the white spaces in the spectrum. As you know, the frequency spectrum is heavily compact with various applications. So what you need to do is you have to just reuse the frequency spectrum again and again, depending upon the vacant frequency slots. Okay, so you can probably you can go in for a startup by developing some proper algorithms to, what to say, to detect the white spaces in the frequency spectrum using a cognitive radio setup. So cognitive radio setup, in the sense, it is not mandatory that you need to have a hardware setup. So my suggestion is that you can go in for a software based startup where you can provide entirely software solutions. Okay, so this is the hardware setup, and this is the software setup. So this cognitive radio setup is nothing but it is abstracted from the software defined radio, which we have seen in the starting stages of this particular presentation. So the antenna, RF, A to D converters, modem, information security, all these things. So you can either contribute in this particular case, or what you can do is you can just contribute in the software section. Software section, you can contribute either in the network layer perspective, the protocol stack, network layer perspective, you can write protocols, or what you can do is you can just concentrate in the baseband layer for signal transmission and reception. Okay, so this is a basic cognitive radio setup. Okay. Okay. Now, if you consider this particular cognitive radio setup in a fading channel, okay. So we have seen fading channel. That is, we have seen this particular system. So this mathematical representation, y of t is the received signal. So if you consider this particular fading signal, so the received signal r of t is given by r of t is nothing but alpha of t into e power minus j theta of t. S of t is the transmitted signal. Alpha of t is the gain of the channel, and all these things are self-explanatory. Theta of t is nothing but it is the phase shift of the channel, and n of t is nothing but the AWGN channel. So what you can do is you can just contribute programs. You can just contribute by writing programs in this particular software programs in using this particular received signal model, and you can analyze the corresponding metrics of bit error rate or something like that. Okay, so the CR system model, it uses transmitter detection. So that is the x of t is nothing but it is the transmitted signal h s of t plus n of t. So in case if the frequency spectrum is vacant, if the frequency spectrum is vacant, so this particular hypothesis will be considered. As we all know that cognitive radio works by spectrum sensing concept. Cognitive radio works by spectrum sensing concept. So if the vacant spectrum is present, so it is nothing but h s of t plus n of t. This is the spectrum, and this is h naught is nothing but null hypothesis, the absence of a spectrum. So the absence of a spectrum decides that there is no frequency spectrum, you cannot transmit and receive. Okay. So what I'll do is I'll just try to let you know how to go in for capacity of a particular the considered case study is a cognitive radio system. I'll just go into the mathematics of how to obtain the capacity of a cognitive radio wireless system, because a capacity is a metric actually. So capacity is a metric. So it is only thing is you need to do some analysis, and you have to do some programming, and you have to provide some solution. That can be the idea of a particular entrepreneur who doesn't want to invest much into his startup and provide end-to-end solutions at the back end side. Okay, so capacity has. I'll go to the previous slides. So capacity, as I have told earlier, so it is a physical layer analysis. Capacity is a physical layer analysis. So like capacity and spectral efficiency. So capacity and spectral efficiency go hand in hand with each other. So capacity is nothing but it is the amount of information content in a particular channel, and spectral efficiency is with respect to hertz. Okay, these information we are all aware of. So probably electronics and communication researchers would know what to say information on this particular. Okay. Okay. Now to derive the capacity of a cognitive radio wireless system. Okay. So we consider a received signal. Received signal. So R here it is considered to be as a vector. So if it is a cognitive radio system, so we consider this channel H. So the channel H is considered to be a scalar wireless channel. So it experiences flat fading, Rayleigh distribution, and n suffix is cognitive radio is nothing but the receiver noise. So it is the PCB noise in the cognitive radio system. So this is nothing but, so after spectrum sensing. Now prior to this, what you have to do is in cognitive radio, you have to do the concept of spectrum sensing. You have to do the concept of spectrum sensing, whether the channel is vacant or not. If the channel is vacant, then you have to transmit the signal. Okay. This is the after spectrum sensing. This received signal model is being considered here. Okay. So this is the received signal for a cognitive radio system in a flat fading channel, and this is the cognitive radio received signal in a frequency selective fading channel. So we can't say that whether a wireless channel is flat fading or frequency selective fading. So it depends upon the environment. Okay. So as a starting point to derive the capacity of a cognitive radio system, so the capacity is nothing but it is maximization of mutual information. So it is maximization of mutual information. So this is with respect to the transmitted signal. D is the transmitted signal and R is the received signal. So this is a simple derivation which we are all aware of, how to find out the mutual information or capacity. Okay, so mutual information or capacity. So with respect to the amount of source data which we transmit. Now this I of D dependent on R suffix COG. So this is nothing but the mutual information. So this mutual information is nothing but it is the difference between conditional entropy or noise entropy or the entropy of the received signal. Okay. So here I is nothing but D dependent on R, which is nothing but H. So this H is actually entropy. So there is a differentiation actually. So H suffix COG refers to the wireless channel. H is nothing but it is here considered to be the entropy. So H suffix RCOG is the differential entropy of the received signal vector, and R suffix COG bar D. So given the transmitted data, what is the received signal? The conditional entropy or noise entropy. Okay. So the received signal entropy is found to be 1 by 2 log base of 2 pi e sigma R square COG. So where a sigma square R is nothing but it is the variance of the received signal. Okay, it is the variance of the received signal, and this variance of the received signal is nothing but it is a correlation of the received signal vector, and H is nothing but it is Hermitian. Okay, so or it is complex conjugate. So you can expand this. You can expand this further. Okay, so replacing R suffix COG. So R suffix COG is nothing but it is this first equation. R suffix COG is nothing but this particular equation. So we substitute here. We substitute this here, and we have R and R Hermitian. So if you want to find out what is the variance of this particular received signal, so you just cross multiply these terms and rearrange expectation. So expectation of a random signal depends upon the probability distribution. So this is a random signal. Noise is random in nature. Noise is random in nature. So it has mean zero and variance one. Likewise, cross correlation of a deterministic signal. So D is nothing but a deterministic signal. It is the data actually. D is the data. It is the deterministic signal. So cross correlation of noise and data. So it is random and this is nothing but zero. So these terms get zero over here. Okay. Then these terms are nothing but you can split up into two deterministic and two random terms. Okay. So continuing further. So as I have told earlier, the second and third terms are considered to be zero as cross correlation and it is independent of zero. So you can just have an expanded representation as in the previous slide, and then you find out what is H suffix RCOG. So you might think that these sort of derivations are, is it essential or it is not essential? So in case if you want to work on the back end side, you need to know what is the theoretical amount of capacity for any particular wireless system or a machine vision wireless system. So all you have to do is you have to just fit in this particular D. You have to fit in this particular D either a data signal or you can fit in either a video signal or an image signal, and you can just do processing. So in the earlier 2 to 3 days of PPT presentation by various speakers, we have seen how to process an image by using neural networks, conventional neural networks, deep learning technologies. Anyway, I'm not going to go into that particular concepts. I'm just going to differ how to contribute on the backend side. How to contribute on the backend side. See, so these are some simple, what to say, simple representations whereby you can provide very good end-to-end solutions. Okay. And if your solution is found to be viable or marketable, then you can have very good profit from your startup in which you plan to start. Okay. So this is the entropy, conditional entropy of the received signal. So finally, it is nothing but this is a noise correlation matrix. So this is autocorrelation of noise actually, expectation autocorrelation of noise, and this is nothing but it is once again it is the conditional entropy of the received signal. Okay, so you have the noise entropy as well as you have the differential data entropy. So you have just substituted. So our objective is to find mutual information. Mutual information substituting 10 and 11 in 4. Substituting mutual information 10 and 11 in this particular 4. 10 and 11 in 4. And using the log A by B representation, log A minus B. So you can simplify further. You can simplify further, and the mutual information of any particular cognitive radio system, which is the considered case study. Okay, so this is actually the mutual information, and if you maximize this over the source probabilities of the given data, so you'll be able to obtain what is the cognitive radio capacity. So this is one metric or one idea where you can develop the or give solution in any startup at the backend side by the concept which you have studied during the course of curriculum or whatever as a researcher or whatever as a faculty we can just contribute. Okay, so for example, so these results have been obtained in MATLAB actually. So the capacity of a flat fading system is being given, so the capacity increases. Okay, the capacity increases for a flat fading channel, whereas for a flat fading channel it is by far very poor. So it depends upon the nature of the channel. So since the channel is random, anyway, I'll explain to you some programs on flat fading channel and frequency selective fading channels while going in for bit error rate, so that you can go in. So you can easily develop some algorithms. So these equations are nothing but algorithms. So these equations are algorithms, and these algorithms will be actually stored into the programmable RAM section of any particular device or any particular personal digital assistant which you want. Even in our mobile, it is possible to cross compile and store it. Okay, so it all depends. This is the graph which has been taken. And in case, as we all know, how to calculate the capacity of a channel. So the capacity of a channel, the well-known formula C is nothing but V log base to 1 plus S by N. So we might have also worked out some problems, or we might have done some laboratory exercises on simulating this particular program. So these sort of small informations can be extended to day-to-day present applications. You can go in for WiMAX, you can develop for OFDM systems, what I can obtain the capacity of an OFDM system. So all these you can provide some end-to-end results actually. So all you can provide some end-to-end results. So this is all well known to us, calculating the capacity of a uh, wireless channel. Okay. Now then we'll go on to the so we have seen the metric of what to say. We have seen the metric of the physical layer, metric of capacity. So we have seen the metric of physical layer capacity. Then we'll now pass on to the bit error rate possibility. Then I'll explain to you some programs which you can be aware of to work on. So as you know, this is a basic digital modulation scheme. This is a basic digital modulation scheme, BPSK. If you transmit this baseband data, so finally, if you process a particular image, so if you break up an image and map it into a number of map the pixels into a number of binary ones and zeros. So converting a binary image into binary ones and zeros. So you can go in for various possibilities, or you can just map depending upon the threshold gray levels. So all the positive gray levels can be considered to be binary ones, and the remaining can be considered to be binary zeros, depending upon the modulation scheme which you are going to work on the backend side. So this is a baseband data, it's corresponding waveform representation. So always the transmitted signal will have a representation. So here it is considered to be BPSK signal, that will be having an energy. So and you'll be having a proper time duration. Okay, so you'll be having energy. So energy is always considered to be the signal to noise ratio. So we have seen earlier capacity. Capacity was in terms of signal to noise ratio. Now, while seeing bit error rate also, this will be in terms of now what to say, signal bit energy. Okay, so you need to have a proper basis function to transmit the signal. Okay, so the performance of any particular system in a fading channel. So the performance of a particular wireless system, so a mobile radio signal, depends upon the nature of the signal transmitted. So flat fading channels. So as we have seen earlier, it is a multiplicative variation. So we can have slow fading channels depending upon the possibilities. Doppler shift, the attenuation and phase shift gets changed. Okay. So objective is you need to calculate what is the probability of error. So the metric probability of error is nothing but, so this is P of X is nothing but it is the probability density function. So you have to make sure what is the probability density function here, whether it is a normal distribution, Gaussian distribution, or it is a Rayleigh fading distribution, and so on. Then you have to consider an arbitrary probability of error. So arbitrary probability of error, and if you just integrate over this particular case, so you may be able to obtain what is the probability of error. It's to be alpha square EB by naught. This EB by naught is nothing but the signal to noise ratio. So P of X is the probability density function of X due to the fading channel. Okay. So this is the probability density function for any Rayleigh fading channel, probability density function for any particular Rayleigh fading channel. So you'll be having the average signal to noise ratio, EB by naught, a signal to noise ratio. There is alpha square is nothing but the magnitude. So the instantaneous signal to noise ratio and average signal to noise ratio. You have to calculate the signal to noise ratio at all the possible time instant. Okay. So gamma is the average signal to noise ratio. Okay. So you have various possibilities. You need to calculate various bit error rate formulas. You have to do some proper derivation. So depending upon the modulation scheme which you are going to consider. So here it is given for the basic binary PSK modulation scheme, FSK modulation scheme, which is available in most of the standard textbooks. So digital communication by Simon Heiken, digital communication by Procase. So all these standard textbooks which you can have. So my particular suggestion is that so you can work on these particular areas and you can provide solutions. So thereby, it is not necessary that always startups need to be hardware oriented. You can also have startups in the form of what to say, a software oriented one where you can develop some algorithms and you can just market. See this bit error rate, probability of error metric. So it is an algorithm actually. or the capacity analysis. So it is nothing but an algorithm. So you can contribute by developing some algorithms in your startup which you develop, and you can market it. There are various clients who are interested in getting possible solutions. This is one way by which you can cater machine vision wireless system startups. It is not necessary that you need to have only solutions through a possible camera or so. So these are some formulas which we are all aware of. So the formula of bit rate of a digital modulation scheme in AWGN channel. AWGN channel is an example for adaptive white Gaussian noise channel, or the PCB noise present in our mobile. So it is the PCB noise present in our mobile actually. So these are the ERFC's complementary error function which we are all aware of. So you can work on MATLAB software or Scilab software or MPLab, whatever might be the software, and ultimately you have to get this sort of metric. You have to get the performance metric of signal to noise ratio in the x-axis and probability of error in the y-axis. So this is for an AWGN channel. So actually you have 6 curves actually here. So you need to analyze how the performance. See, signal to noise ratio, as you know that it is a dimensionless number, but here for analysis it is given as a number in decibels. Okay, only for analysis it is given in decibels, whereas it is a dimensionless number. Okay, 10 watts. So 10 watts will be converted into what to say, dBm or dBW or dB watts or whatever might be the case. As we have seen some problems earlier. For example, if you want to find out the best modulation scheme, okay, so if you take the probability of error of 10 power minus 2, so this particular graph, it reaches the signal, has a signal to noise ratio of 4.2 dBs. So 10 from 10 power minus 2, if you proceed here, this comes around the 10 power minus the 4.2. And if you proceed further, this blue color line, it reaches at 7.4 or something like that. So it takes more signal to noise ratio. This particular red color line, it takes more than 10 dBs. So if you compare these three graphs, so this particular graph, which is nothing but the BPSK. So either by using formulas you can obtain, or by using MATLAB programs through simulations, trial and error method you can obtain. This particular curve gives very good, what to say, very good, or it uses very low signal to noise ratio. So the objective is to reduce the power. So if you reduce the signal power, so if you develop some good modulation schemes, in your startup, so that can be a very good idea where you can work on for any particular application and you can just market that. So these are all some low cost startups. So low cost startups if you work possibly on the baseband side. Okay, so this is how you need to compare the metric of signal to noise ratio and probability of error. This is in the case in an AWGN channel. Okay, likewise, what to say, so mm, you'll be having the wireless transceiver performance for a single input single output system in multipath fading channels. So here, see, if this is for the case of BPSK signal. See, earlier in this graph we saw in the previous slide, so it came around a 10 power minus 10. Okay, so this is for BPSK. So this curve is considered to be for also for mm, considered to be for BPSK. Likewise, you can also obtain the graphs for the flat fading channel and the frequency selective fading channel. So if you compare these three graphs, so the first graph, as we have seen earlier, so around 7 dB, 7 decibels. So you need to spend only 7 decibels power to transmit a signal in an AWGN channel. But as we know, AWGN channel is not a practical channel. AWGN channel is not a practical channel, and these are two practical channels. So you have to spend more amount of power. So you have to spend around more than 12 dBs for this particular modulation scheme. You have to spend around 13 dBs for this particular modulation scheme. So you can develop some good algorithms and you can assess the performance by using a proper probability of error metric. Okay. So now what I'll do is I'll just try to explain a program to obtain these particular graphs so that it will be easy for you. So one second, I'll just stop my sharing and I'll just try to share my another program. One second. No, stay connected. This is one second. I'll explain the program for obtaining these graphs. Okay. One second. See if my screen is not screen is sharing. Window. So good evening, Badri sir. Is my program screen visible for you?
Yes, sir. Yes, sir.
Okay. Thank you, sir. Thank you. See, thank you. So earlier we have seen what to say. So earlier we have seen this graph actually. So we have seen earlier this particular graph. So now let you know a small program to develop a program of this particular type. Probably many of us will be aware of that, or you might be aware of this particular program, which I'm going to explain now. But anyway, it will be just an information provider. So you can work on this particular program. So this is nothing but an algorithm actually. So this is a small program which has already been done for BPSK modulation scheme. Likewise, you can contribute in any modulation scheme for any particular application. Okay, so you can go in for OFDM, variants of OFDM, IMO, OFDM, all these information you can just go in. But here I'll just explain with just a small programming segment. So here in this particular test bed, so I consider some thousand bits. So actually, for doing simulation, you need to consider what to say, more than 10,000 bits, random bits. Okay. So I define a variable data PSK is equal to rand src of 1 comma n. So now so this is program actually, it can be executed in MATLAB actually. So you can run this program in MATLAB. So of course, I'll just explain the program. Probably if you are aware of MATLAB, you can just execute and see. So I define a variable data PSK is equal to rand src of 1 comma n. So this will generate one-dimensional row vector of 1000 bits. Okay, and I define noise to be random of 1 comma n. So random will generate random numbers following normal distribution with mean zero variance 1, and so we are generating random noise. So this is nothing but actually this program. So this command line is actually intended for defining the noise. So this is nothing but this is the signal signal data transmission. This is a data signal transmission. This is a data signal. So this is a data. I give a command line. This is data signal transmission. Then this is nothing but this is a receiver noise. So this is receiver noise. That is probably AWGN noise. AWGN noise. Okay. So our objective is we need to consider y of t is equal to y of t. That was what we saw. Y of t is equal to h into s of t plus n of t. That is what. So this n of t is nothing but this receiver noise. So this n of t is the receiver noise. N of t is receiver noise, and this s of t is nothing but it is the data signal transmission, and h is nothing but the channel actually. So now what we do is we'll initialize signal to noise ratio. Signal to noise ratio is nothing but it is EB by N naught. EB by N naught, or this is nothing but it is nothing but SNR. EB by N naught, or it is nothing but SNR. So so we initialize the signal to noise ratio value to be by using a for loop. By using a for loop, we initialize the signal to noise ratio 0 to 30 values. And in case if we want to display the signal to noise ratio in MATLAB, so we can give us the loop command exactly next again. Then next is nothing but so the signal amplitude. We define signal amplitude PSK another variable. Square root of 10 times the anti-log of the signal to noise ratio values multiplied by data PSK. Now this data PSK will actually generate plus ones and minus ones. Data PSK will generate plus ones and minus ones, and we are just giving energy through this. Okay, So you might think that why it is there actually. So this is actually given to, so S of t is nothing but, S of t is nothing but, S of t is nothing but, so this actually square root of, what to say, square root of 2 times EB, 2 times EB by N naught. This is square root of 2 times EB by N naught, square root 2 times EB by N naught, and this is multiplied by cos 2 pi FCT. FCT. So cos 2 pi FCT. So this cos 2 pi FCT is nothing. So this cos 2 pi FCT is nothing but, what to say, this cos 2 pi FCT is nothing but it is the signal, data signal transmission. Cos 2 pi FCT is nothing but this data transmission and this energy. So this 2 square root of 2 times EB by N naught, or this EB by N naught you can have. EB by N naught is nothing but this particular value. We are giving energy. So we are defining the signal model here actually. Now we are initializing trial and error. Actually initialize Monte Carlo runs. Actually Monte Carlo is a place in US which is famous for casinos, whereby you'll be having, whereby they were playing games of chance. Considering Monte Carlo simulation runs, Monte Carlo loop actually. So we take 100 Monte Carlo runs. What we do is we define an AWGN channel. So this is an AWGN channel defined. From this, we have the receiver. So from here to here, you have the transmitter. From here to here, this highlighted one. From here to here, you have the transmitter. Then from here, you have the receiver. From here, you have the receiver. So the receiver, this is the received signal model. This is the received signal model. This is received signal model. So R is nothing but S of t plus N of t. So here H is considered to be 1. So here we have seen this particular slide actually. So this particular slide, so this is the transmitted signal for any wireless system. So whatever might be the system, this sort of a representation will have. You'll have this. So you can write programs based on this. So wireless transmitted signal S1 of t either. This is cos 2 pi FCT, which we saw in the program earlier. Then what to say? To show the signal representation case. So y of t is nothing but x of t plus n of t. This is the AWGN channel. So we are seeing the AWGN channel actually. We are seeing the AWGN channel. So that is what I have written here. So received signal model for AWGN channel. AWGN channel. AWGN channel. And next is nothing but after the receiver. So this is actually baseband simulation. We are not multiplying any carrier. So this is actually baseband simulation where we don't use any carrier. Straight away we just transmit and receive the signal. We don't use any physical carrier here. So you can also use a physical carrier and you can transmit and receive actually. Okay. So the received signal is less than this particular threshold. So this is the what to say, the decision parameter for a BPSK modulated signal. Likewise, you can have for various modulation schemes. You can have for various modulation schemes. So you can have either +1 or -1. So if it is less than 0, it is -1, and if it is greater than 0, it is +1. Then you calculate the number of errors. Okay, so you compare the decision device and you compare the decision device through decision variable. So that is decision is not equal to data PSK. Decision is not equal to data PSK. So if you compare these two, these two, so if it is if it is not equal, so the error is incremented. So we consider error. So this 1 by n row vector and this 1 by n row vector are just compared. 1 by n row vector and 1 by n row vector are compared. In case if there are errors, the error is appended and it is incremented. So the bit error rate for each and every Monte Carlo runs. So we have defined some Monte Carlo runs here. So for each and every Monte Carlo runs, the bit error rate is calculated. So the bit error rate is nothing but error by n. So comparison of various bits and you calculate the bit error rate. Now for various signal to noise ratio, for various signal to noise ratio, you can calculate the signals, the probability of error or the bit error rate, and you can just make a plot. So this is a small programming segment for AWGN channel. So small programming segment for AWGN channel, so which we can just work for any modulation scheme. at the back end. So this is or at the back end. So then this is semi-log y. These are all self-explanatory. Then what we'll do is I just help you how to simulate flat fading channels. So from here onwards, we have the concept of flat fading channel. So the flat fading channel. So we have the concept of a flat fading channel. So n is nothing but once again we consider this to be 1000. So it is the same setup actually. So we consider once again the data to be rand SRC of +1 and -1. Then the SNR value is considered to be 1 to 30. So amplitude is defined once again. Then we define MCR. This is the Monte Carlo runs. We define error. Now this particular entire programming segment is mainly for this particular programming segment is for actually what to say. Particular programming segment is for the channel. Is for the channel. So we know that the channel is nothing but this end up to here. It is nothing but the uh, programming channel. So alpha h is nothing but alpha into e power minus j theta t. Okay. So in the PPT actually we have seen y of t is equal to alpha of t into x of t into e power j theta t plus n of t. Okay. So x of t is the transmitted signal. Alpha of t is nothing but it is the channel gain, and e power j theta is the phase response. So this particular equation is only written here in this particular program. This particular equation is written here in this particular program. So alpha norm dot star complex uh, PF. So cos theta minus sin theta, e power minus j theta is cos theta minus sin theta. Either you can have positive phase or negative phase. Okay. So for that we define what to do is we define to calculate what is alpha. Okay. So alpha norm. So here alpha is normalized actually. So alpha is nothing but root of x square plus y square or y1 square plus y2 square or whatever it is. So it is the square root of x1 square plus y1 square. Okay, that is alpha. And then for that we define two noise values. We define two noise values. Since channel is considered to be complex, we consider complex noise. So all these inbuilt commands are available in MATLAB. So this is written in MATLAB actually. Okay, so so then we are just normalizing noise. So normalizing noise in the sense for the corresponding distribution. So if it is mean 0, variance 1. So if it is mean 0, variance 1 for normal distribution. Likewise, you can have for Rayleigh distribution. Okay, and this is nothing but the e power j theta term. So PF is nothing but it is the phase term. PF is given for the phase term. Okay, so this is as you can see PF. So cos theta cos theta minus sin theta. PF is nothing but the phase term, cos theta minus sin theta, cos theta minus sin theta. So you can just substitute here. So all these mathematical expressions are written as MATLAB programs. Are written in MATLAB programs, and or you can just write in C language, or you can just do cross compilation, and you can import it or dump it into your particular intelligent device, your mobile or whatever might be it is. So if your mobile supports MATLAB, you can just work on these particular programs. So these are all some simple programs. So you can have a very good startup by working on the back end side if you have very good knowledge in the particular field of wireless communications or digital communication or whatever might be it. So this is one possibility of exploring. Okay, so it is not necessary that you have to write programs only in C language. So you can just write programs in MATLAB. You can just do cross compilation, and you can do convert it into an assembly language program, and you can just market it. That will be a good way of making money for a particular startup. Okay, so this is the corresponding channel. So then you normalize the corresponding channel. So alpha norm, you normalize the corresponding channel alpha norm. Then h is nothing but it is alpha into e power minus j theta. Okay. So and then r is nothing but it is the received signal. R is the received signal. So received signal h is h into AMP. So h into AMP plus C noise. So noise is nothing but the complex noise. Then what we do is we just take the decision. So since it is a BPSK modulated signal, we just take the decision depending upon this is decision making. This is decision making. So this is a decision making. So this is actually your correlator. Okay, this is your correlator decision device. The correlator decision device. Okay. So in the in the PPT presentations, we have earlier seen various possibilities. Okay, so various possibilities. See, any wireless transceiver, if you work on the back end side, you will be having the correlator, or you'll be having the match filter, or the envelope detector or decision device. So the decision device is used here actually. So this is actually a baseband level contribution at the back end. So just work on providing a possible solution. Just explaining to you this particular program so that you'll have a real idea of how to go in for a startup with the wireless system based machine vision concepts. Okay, you take the decision device. So similar to previous problem, so this is also BPSK. You compare the decision vector and the data vector, you calculate the error, then you find out what is the bitter rate. So bitter rate is nothing but so bitter rate here is nothing but actually the number of errors in comparison, errors or number of errors in comparison between transmitted one and the received one. Okay. Okay. So then you calculate what is finally the probability of error. So this is simulation way of calculating the probability of error. So you can have the x-axis value, you can have the y-axis value, then you can find out what is for the case of, this is the flat fading channel bitter rate actually, flat fading channel based bitter rate obtaining. Then next is you have the other possibility which I'd like to let you know is the third program is nothing but the frequency selective fading channel. Third program is nothing but it is the frequency selective fading channel. Frequency selective fading channel. So you can try to have a bitter rate of frequency selective fading channel for any modulation scheme. Okay. So we consider the same procedure. N is 1000. We have y is equal to rand SRC. Define the signal to noise ratio. Then we define the transmitted signal. So same thing, it is not at all difficult. Only thing is if we follow some certain steps, you can either work this in either Simulink, or you can work either in MATLAB or Scilab or whatever software. But the important fact is that so you have to do cross compilation, or you can, or if you write in C, it is well and good, or if you do in assembly language, it is well and good. That is what industry demands. So your startup can be an outsourcing unit. So these are all some low cost ideas with this particular example modulation scheme. You can develop some modulation schemes of your own by doing some small variations. So, and this is, as I said earlier, this is a frequency selective fading channel. So the frequency selective fading channel, this is for example, a COS 207 channel. So you can obtain the power delay profile. You can obtain the power delay profile from any very good literatures. So if you just Google it on in Google, you'll be having very good power delay profile for any particular frequency selective fading channel. So the time instants are taken. So the power values are obtained. The time instants are taken. The power values are obtained. Then this procedure it needs to be followed. So you have to select random paths. So since these are some time and power values, so you have to select some random paths. You have to select some random paths, and you have to select some random parts, and you have to obtain the coefficients. Now this actually a tap coefficient here, it is given as 51. Now this is calculated based on the number of what to say, the length of the power delay profile. So this is actually a initial setup calculation. So the tap coefficients are found out, and the non-zero values of channel response, non-zero values of channel response are filled in here into these tap coefficients. So we are converting this into a proper integer like representation, not fractional one. Then we add all the powers for each and every path. Then we find out what is the impulse response value. We find out what is the impulse response value. This is the normalization square root of the total power. And in case if you want to observe in frequency domain, you can take its FFT. So only thing is, so you need to know some concepts of wireless communication, digital communication. You can also give some very good solutions. This is one way. Okay. Then once when you have done with the channel values, once when you are done with the channel values, then you have to go on to the system model. Then you have to go on to the system model. So the the system model. Um Uh, you generate noise. So noise has to be a complex noise. So noise has to be a complex noise. We select two values. So since it is a plus jb, so complex noise is nothing but it is normalized to noise values. Then the received signal. So this is the received signal model. So transmitted signal multiplied by its frequency domain representation, or you can have its time domain representation. So okay, then you add the complex noise. Then this particular term, this is nothing but actually equalization. This is nothing but equalization, removing the noise components. Okay, removing the, this is equalization actually. This is equalization, removing the channel components before taking decision. Before taking decision. So this is also used in the previous program. So equalization, removing the channel components before taking any previous decision. So what to say? So this is also equalization. So R is nothing but conjugate of X. So cancelling out the effect of, this is equalization actually. This line actually equalization. So this is equalization. It needs to be done to remove the effect of the channel. Okay. So this is for a frequent selective fading channel. So since it is a BPSK modulation scheme, so after removing the effect of the channel, you take the decision. So if it is greater than 0, it is +1 or it is -1. Likewise, each of the modulation scheme, the threshold differs. So if you just change the threshold for any modulation scheme, you can write some very good programs in any language. Obviously, of course, it is, if it is MATLAB, you can easily cross compile using a cross compiler, or you can just write in C. Okay, so then you need to find out what is the, you need to find out what is the error. You need to find out what is the error. Then you have to find out what is the probability of error for the corresponding frequency. Okay. So this sort of programming, small programming, you can work on to develop some solutions for any modulation scheme, or as I said earlier, uh, for system architectures. So while seeing the earlier slides, I've just given the option that for any machine vision based wireless transceiver setups, so you can work on either the modulation scheme or the system architectures. So for BPSK, I've explained to you the program, so which we are all aware of. Likewise, you can go in for OFDM, or you can go in for any standard application or whatever modulation which you deem to work on. So this is one possible way of providing solutions by an entrepreneur, and in case you can have a good startup, low cost startup. Or so this is in the baseband section, or you can also work in the RF section. That is what I intend to convey from my uh, lecture of going in for machine vision based wireless system startups. Okay, so this program, so probably you can work and you can execute these programs. Okay, so as you know, this is the wireless system. Now it has gone to, people are talking about 6G generation. So for various generations, the ultimate thing for any application, starting from wireless LAN or personal area network or whatever might be, is so you can either work in the baseband section, or you can work in the what to say, in the RF section. Okay, so the baseband section, you'll be having physical layer concepts. In the RF section, you'll be having fabrication of all these concepts. So this is just well-known information. So you can go in for data rate based applications. Okay. So finally to conclude, so I've introduced to you the various possibilities of providing solutions in a startup, in case if you go in for wireless system based machine vision startups. Okay, so the founder of a startup needs to know the market validation. So market validation, in this case, you need to know what are the metrics: capacity or bit error rate. You can do some variations on capacity or bit error rate. So identify the problem. So the problem here is finding out a good modulation scheme. So the problem which I have given here, the problem which you can have is a good modulation scheme, or what to say, a system architecture. then solution is nothing but the performance metric. So that is what I intend to convey. And building a minimum viable product. So by minimum viable product, you can go in terms of RF, and then you can go in for validation. See, validation you can do either by testing in the RF section, or by you can do validation by deriving some good system model derivations for finding out any metric like capacity or bit error rate. Okay, so that are all the pros or advantages of this particular machine vision based wireless system concepts. Then you have tax exemptions for startups. So if you look into the Startup India website, so there are various exemptions if you get your startups to get registered. So it is coming under a particular section of Aicte. So if you just search for that, you can have a very good benefit there. Then regarding the cons of disadvantages of the startups, what I would like to say is, so as you know, startups are they are temporary business models, and to make that those temporary business models scalable, it is you need to have proper seed fund, you need to have a proper investor, you need to have a good solution. So sometimes it might, most of the times it might fail, or sometimes it might fail. It depends upon the effort, the considerable sustaining effort which we do put actually, the considerable sustaining effort which we do put actually. Okay, so sustaining effort is especially challenging, so high rate of failures are possible. Okay, so this is what I would like to conclude from my side. So these are the pros and cons. Okay, so regarding the startup schemes in state government and central government sectors, as I illustrated in the previous what to say, and in the previous presentation slide earlier before, during the start of this lecture, um, so you can have uh, funding to get obtained from various organizations. So you can just look into this particular website, Startup India status report. So they'll give very good information about startups. Okay, what are all the incubation industry academia partnerships, and as you know, the government is promoting women entrepreneurship. So the startup policies of so women entrepreneurs. So women entrepreneurs are encouraged to have startups. So they are given actually 20,000 per month. Actually 20,000 per month for a period of 1 year initially. So women entrepreneurs are motivated, are given the benefits of coming up in their lives. So that is one possibility. Okay, so you have Atal Innovation Mission. So Atal Incubation Centers. So various possibilities are there for going in for startups. There is National Innovation and Startup Policy. So many institutes have registered in National Innovation Startup Policy. So you can explore all these particular possibilities. So this is what I would like to convey from my slide. So probably I would like to conclude my slide. Thank you. So in case of any doubts, so thank you for your patience. So I'd like to conclude my slide here. So
And thank you, sir. The session was very informative, sir. Thank you so much, sir. And once again, I thank all the participants, those who have participated here, and thanks for your patience. And we are posting the feedback form. So before leaving the session, just fill the feedback form, whichever posted in the text box. Is there any other doubts? Is there any other doubts?